if it's fine. So this is IIT. Okay, then we have to just do these other questions. So this is question 56. Okay. So this matrix A, 4 by 4 matrix. Yeah. So the question would be to find the determinant. So yeah. So please tell how to compute the determinant.
Okay, we can do like row operations and we can reduce this matrix. After that, we can complete.
Okay. Okay. So maybe take a few steps and see where it goes and tell us, because I would want to avoid, means I would want to see if I can do it without questions. But so which particular row operation do you have in mind?
Subtracting one row from another.
Yes, yes, but which particular row? Is it a planned decision? Yeah, I suppose, yeah, maybe that's not so bad, right? Uh, yeah, and then it becomes a 3 by 3 thing, for which you can find. Is there a better way? Anyone has an idea of any better way? And it's the same thing. I will write like this. I think this looks better. I'll start to write x. So see, I mean, if it's clear that this will have the same determinant. So computing determinants is a very important problem that keeps coming up in various areas. So do you see why this is fine? This is just subtracting the column. Yeah, I think it's just that kind of process. So it's not a very interesting question, right? Yeah. Okay. However, we can pose the following question. I think that we can try. So I'm just erasing this because we understand that we can just do it. But can we find a closed form for the following? Now, just a generalization. So as it was in that one, that is x plus 1 on the diagonal and x plus 1 everywhere below and x everywhere above. So there should be a closed form for this kind of thing, right? So can we figure out this thing? Maybe we will say Pn. Yeah, any ideas? Is this correct? Anyone? Yeah, this looks correct, right? No? And if you follow this, then it comes down to P1x. And P1x is just x plus 1. And let me check with two variables. Indeed. That is something which we can say is nice, right? that all these so the answer to the previous one was just 2021, and all these things have determinant 2020 x plus 1. Okay. Any questions? Is it fine to everyone?
Yes.
Okay. Yeah. Srijani, is it fine? The recurrent, the means the recurrence, it's not even a recurrence, but I mean, hello?
Yeah, it's fine.
Okay. Yeah, probably it's too easy, but yeah. So I mean, the point is that the point is sometimes we can do these things, sometimes we can do these things, and you can just by going to the abstract case, you can actually learn. Uh, yes, yes, yeah, we cannot hear you. Yeah. Yes, Srijani, so no, you're not audible. Your audio seems to be connected, but you are not audible. Not to me. Can anyone hear Srijani? No,
No, no.
no. Yeah, you should check because you might be speaking, but what do you say? I mean, the wave that doesn't show, so it's not. Yeah. So, but it would be nice if we can also hear you. So, yeah. But anyways, this is a small thing, and so see, do not never underestimate determinants and identities, and these are very wonderful things, and they will keep coming up even if you're doing algebra or you're doing geometry. Some nice form will always be related to determinants. Okay. In fact, the last day there was a determinant identity that our whole class no one could do. I also cannot yet do. So, but it's very very important. It's related to some some quantity being intrinsic. Yeah, intrinsic geometry. I mean, intrinsic to the geometry of a manifold. Okay, and that determinant, computing the determinant actually proves, but we are not able to do it. Okay, and as you can see, it's not mindless calculations. It has it. There are many different ways to approach it. Okay, right. Okay, so I hope we learned something. It's easy, and also maybe one more interesting thing is that. It's a very general thing. I mean, just notice that this is a very general thing. You could place anything here and the answer would. Yeah. It's a very interesting thing. I mean, yeah, the determinant doesn't depend on the dimension. Okay, so let's move on. Let's move to these problems will be there. Yeah, let's move to problem 57 then. It's a integration question. So you have to compute the limit of an integral. Sorry, this should be. So here, before you think, I'll just say that this this is a sequence of functions. This, and you have to compute the limit of the integrals. So these will be all numbers, and you have to compute the limit.
Is 0 is the answer?
Why?
I just integrated simply. Then I put infinity in the place of n.
Okay, you integrated this.
Yeah.
Okay, so what is the integral?
Minus 1 by n.
Okay. Hmm.
E cos n, ब्रैकेट के अंदर e cos n
E cos n. Okay.
minus 1
Minus 1.
minus 1 bracket बंद
Okay.
minus 1 by n integration
Mm-hmm.
0 to 1
Mm-hmm.
2x
2x.
e to the power x square
Okay.
cos nx dx.
Cos nx dx.
तो
Right.
दूसरा वाला पार्ट का वैल्यू 0 to 1 के अंदर 2e के बराबर आ रहा है.
This one.
हाँ.
But you see, there is no need to integrate that, right? You're going to take the limit, na?
हाँ.
I'm saying that you don't need to integrate this. You don't need to know what the value of that is.
हाँ नहीं किया.
Ah, good. Okay. Right. So now when you take the limit, it's clearly going to be. So that's the point, as Arnab has done, I suppose. That's the nice point, right? That once you have the 1 by n, you don't really need to integrate this. Because you know when you take the limit, it's going to go to 0 because this thing is going to be a bounded quantity that you can prove by any way you want. Okay. It's bounded, uniformly bounded by some m. So the answer is 0. That's wonderful. That's how it should be. Yes. However, this problem is saying something. So maybe I can share you this perspective and then you can look at it later. But the solution is done, and that's a thing. It's one thing. But what this is trying to do, if you think about it, it is trying to break the function. So if you think about this function fx, uh, just think about this function fx equals to e to the x square. Okay. And now think of this function f from, you think of it from 0 to 1 to to r, correct? Right. But then you can also think of this as a function from the circle, though it is not needed, but a circle is very naturally periodic thing. So there is an alternate way where you don't have to go to the circle, but you can just think of it like, oh, no. So that's not correct. But then I will need that it is equal at 0 and 1. Then only I can think of it as a function. Circle. Never mind. Then we will change the approach and think of it like this. That's why the x square is there. So now you think of it from minus 1 to 1, and now you can see that it will be something like this. Correct. Right? And now what you do, you forget the other parts where the function was e to the power x square was defined. So we're not looking at the sine x right now. The sine x will come. That will be some Fourier coefficients. Okay, but that's not the point. Point is that you just periodically extend the function. First thing. Okay, and just keep extending it. So, right. So this. Now, say this. Right. Now, the desire is to look at this function x square and somehow break it into this thing, which you may have seen. These are called the Fourier coefficients, right? See this. No, this cannot be correct. Wait, just usually it's on 0 and 1. This is not, I mean, this cannot be periodically extended if you look at it from 0 and 1 because it doesn't match at 0 and 1. So this is a function from -1 to 1. And then just a minute. If it's a function on -1 to 1, if I want to write it, just a minute. Okay. So what is the period of sine x by 2? Right? 4 pi, right? So maybe we will put pi x, right? So the period of this function is 2, right? So cos pi x, the period is 2, right? Because you just do it, you will see that this is same, right? So you see this is a function which has period 2, and this is the way we have defined it now. This is also a function which has period 2, right? So but we would want to write this periodic function which has period 2 in terms of these fundamental periodic functions sine and cosine, which we are for convenience writing it using powers of e. Okay, and we will want this thing. I mean, we want this. We don't even know if this kind of thing exists, if it's possible or not. We want these CNs. Okay, so now if you just think about it, how will these CNs be obtained? Right? Just if you think a little bit, then you will see that these CNs would be obtained like this. With some factor here that you can also figure out, right? Because you have to take this function e to the power x square, multiply it. When you multiply it by this, right, then this term vanishes, right? And then when you integrate this Cn, you recover with some coefficient, basically with 2, because 2 is the integral from -1 to 1 of the constant function 1. But the upshot is that if you look at the other terms, like some Cm, right? Now you see, now this becomes n minus m pi x. And this integral, if you do from -1 to 1, this is 0. And that's the point. You other terms vanish, right? And that's why this gives you Cn. And this thing is precisely this. I mean, this is the real part of it, right? More or less. I mean, pi is there, but you can probably manage it somehow, right? It's the real part or the imaginary part, something. Correct? Okay, now if you assume that this is possible, which should be, I mean, e to the power x is a nice function. The only problem it has is unboundedness, but we are in a bounded interval. So this should be possible. Some general theory for analysis will tell you it's possible. But if this is possible, then you know that this Cn should go to 0 as n goes to infinity. Yes or no? Right? When series is converging, the terms should go to 0. In fact, much more should be true. But let's not get there. Its terms will go to 0 is clear. And that's the answer to the question. That the limit goes to 0. Right? Okay. So that is the point. That is the meaning of the question. That these are the Fourier coefficients of a function for which you have the Fourier inversion formula. Okay, so you should read about this. Stein and Shakarchi has written a very nice book, which is the first book, so it's on the very easy side. And you should read chapter 1, some for Fourier analysis on circle. Even Baby Rudin has a chapter on Fourier analysis, so you can read from there also. Stein and Shakarchi, Fourier analysis. Very first book, I think, in that series. And chapter 1 has Fourier analysis on circle. This is about that. It's a very interesting field of study. Okay. Then you can get idea of this kind of questions. So all these questions have meaning. I mean, they make it in a meaningful way, but right. Yeah. Okay. So yeah, I think we will stop here with these problems. And is that fine? Right. And then let's meet and do some, try to do some field of fractions localization. Okay. Yeah. But check this out. I mean, because study Fourier analysis, then you will get the motivation for a lot of the things you do in analysis and will do in analysis. Okay. Yeah. Right. Yeah. So yeah, I'm ending the meeting. Is that fine? And then we'll meet in some less than 10 minutes, and we will start with localization. Okay. Or continue with localization.